This presentation is delivered by the Stanford Center for Professional Development.
So, well, I'm guessing by the fact that I can see myself that we're on. So, hey everybody, and welcome back to CS106B. My name's Keith. I'm a section leader here. I teach CS106L, which is the standard C++ programming laboratory. So, I recognize a few people here, which is great. And Julie wanted me to come in today and talk to you about the C++ programming language. What's it look like outside of CS106B? What sorts of things you need to be aware of? To just kind of give you a general picture of what this language looks like. And before I get into the actual C++ stuff, I wanted to start off by congratulating all of you for making it through this class, because that's not a small accomplishment. If you think about where you started, day one, probably looking at this screen right here, going, what's that pound include? What's a genlib? And what's cout? And why is it really, really less than something? Well, look where you are right now. You now know how to be a client of the vector, the stack, the map, the queue, and the set. You know about recursion, you know pointers, you know linked lists and binary trees and graphs. You know algorithmic analysis and graph algorithms and searching and sorting. You know how the lexicon works. You know how to implement all these classes. You know data abstraction. That's not a small accomplishment. That's really something to be proud of. And what I wanted to say is that these are real practical tools that will follow you no matter where you take them. Some of you might go on CS. You might think, wow, I really like this class. I want to see where it goes. And that's great. And no matter where you take it, if you go and take algorithms, you take compilers or databases or operating systems, the skills you've learned here really is going to make the foundation of all of your programming. You're always going to be using maps. You're always going to be using vectors. You're going to need recursion no matter where you apply it. And it's really wonderful that you have these skills. And of course, some of you aren't going to go on in computer science. That's totally fine. You know, took this class and not for me, or, you know, maybe not. Well, that's fine too, because whether you go into sociology or philosophy or psychology or math or physics or chemistry, there are problems to be solved. And there's problems you can solve with a computer. And what you've learned in this class is the most valuable skill of them all, which is how to take a problem, model it, and solve it. And that really is something. The skills you've learned here transcend any specific programming language. You can do everything you've done in here in Java, in C++, in PHP, in Python. Any language you think of, you will be using these same tools. Now, that said, we've taught you everything in this class using the C++ programming language. And we use C++ because it's very good for expressing the concepts that we were going over. It has great support for recursion, has exposed pointers, so you can do things like linked lists and binary trees quite nicely. It has objects, so you can do data abstraction. It's got templates. It's a very good mix of different programming strategies and different programming styles that means that we could teach you things without having to bog you down in language syntax. That said, this really hasn't been much of a class in C++. Think of it as like we all put you inside the C++ bus and drove you up to the top of the mountain of CS106B knowledge. You know that, yeah, the bus got you up there, but you really don't know what's going on under the hood. But that's OK, because what you've learned in this class is more important than that. All the programming language knowledge in the universe is not going to help you solve a problem if you don't know how to use a vector, you don't know how to use a map, and you can't make a recursive function solve things. What I want to do today is talk about what the C++ language is. What's it look like in the real world? What kind of stuff do you need to know? And more importantly, just how to take these skills you have learned, which are very generic, and go and apply them in this language. Now, I love C++. I've been using it for years. I think it's a beautiful language. It's got support for so many different programming paradigms. It's easy to use once you get kind of a hand on it. It lets you solve problems in so many different ways. And really, I just want to go show you what's it look like. Kind of think of this as like an appetizer. I'm just going to give you the plate. Like, you know, this is the C++ appetizer plate. Show you a little bit of this, a little bit of that. Kind of give you enough working knowledge that you know where to go to get help. So you can see this is what you need to learn. Kind of get an overview of what we've been doing, what we provided you, what we haven't provided you, so that by the time you're done, you can think, you know, maybe I want to go on in this language. Now, I'm not going to force you to learn C++. I can't do that. I mean, I'm not going to like follow you around. Did you learn C++ yet? Did you learn C++ yet? No, I'm not going to do that. Really, you guys are all competent programmers right now. You know how to solve these problems. You know how to take on these challenges. And so I just want to show you the language so you can decide whether or not you want to pursue it. Maybe you will. That'd be great. If not, well, that's OK too, because you know how to tackle problems, and all you need now is a language to do it in. Now, I want to show you basically 4 aspects of C++. First, just some philosophy and some history, because every language has a personality. Every language wants to treat you as a programmer a different way, give you different options. And so I just want to show you what you should expect when you're working with C++. Because as a language, it has a lot of criticisms. How many of you here have heard bad things about C++ in any way, shape, or form? OK. Wow, every single person in this room, basically. OK. So yeah, there's a lot of criticisms leveled at this language. And what I want to do is kind of to show you what's the mindset so that you can take a look at these criticisms and kind of reevaluate them. Because in all seriousness, most of the criticisms leveled at this language are criticisms of things the language doesn't try to do. But at the same time, if you get this philosophy and you get this history, you'll understand where this language came from, what it's designed to do, and where it's going. The second thing I want to talk about is just the actual mechanics. Just what does the programming language look like? So I'll talk about the libraries. I'll talk about the core language features. What happens when you take away things like genlib and simpio? What are you going to have to do now that you don't have those? Turns out, it's actually pretty straightforward, and you already know most of it. And then some language features we didn't cover, things that you would expect to see in a professional setting that we just didn't go over in this class because it's needlessly complicated and just doesn't have much to do with these general data structures and algorithm challenges we've been giving you. And finally, just some references. Where to go? You want to learn C++? Great. We have a list of wonderful books and resources you can go and reference, and it can get you up to speed very quickly. So that's kind of a game plan. See what's out there, have some fun with it, and then learn where to go. Sound good? OK. So I want to start off with a quick history of C++. So C++ did not come into being one day when a whole bunch of programmers came into a room, made some demonic incantations over a bubbling cauldron, and walked out with the language. That didn't happen. It was not invented in one day. People did not sit down and say, our language is going to look like this, and this, and this, and this, and this. It has a history. It has evolution, and you can see different traces of, wow, we tried doing this, didn't work, let's go do this. Let's go add this feature, etc. And it started off, wrong direction, with this guy. So I will attempt to pronounce his name. It's Bjarne Stroustrup. I've been told that the way to pronounce this is to say Strustrup with a Norwegian accent while cramming a potato down your throat. I'll just get it close. So anyway, he's a Danish computer scientist, and he was getting his PhD in computer science from Cambridge. And his specialty was in distributed systems and operating systems. So his goal was, let's take some problem, spread it out over several computers, have them communicate via network protocol, and get some results. And he chose to write this program in a language called Simula. And I confess, I don't know much about this language. I haven't heard anyone using it. But back then, it was this object-oriented language, and he said it helped him think about the problem. It had classes, so you could build a computer object, a protocol object, a network object, and they'd send messages to each other the same way that a physical computer, a physical network, and a physical protocol would communicate with each other. Got it working pretty fast and ran it, and much to his surprise, found out that it was so abysmally slow he could get no practical results out of it. Question is, what went wrong? Well, it wasn't his program. It was the Simula language implementation. He actually ran a profiler on his code to figure out why it was going slowly. 80% of the time his program was running, it was doing automatic garbage collection, even though he was doing all his own memory management. So think about this. You spend several weeks writing a program, you run it, and for every line of code you're writing, 4 lines of meaningless code that someone else wrote are also executing. That's really slow. So we had to change approaches. He went and rewrote this entire program in a different language called BCPL, which is related to C and the B programming language, which came before C. And of course, it's very low level, it's very fast, but it didn't have these nice high-level features in it. And he got it working, but it took a lot of time. And when he was done, he decided, you know, I'm never going to tackle a problem like this again until I have a proper tool for the job. He ended up at AT&T Bell Labs, which is the same place that the C programming language came out of. In fact, he knew Carrington and Ritchie, who invented that. And he came up with this language called C with classes. It was a precursor to C++. And people loved it. It combined the best features of Simula, which is that it's object-oriented design, with the best features of C, which is the runtime efficiency, into something that was fast, flexible, and helped you think about problems. And what he would do is work on this implementation. He had people actually using the language, and when they needed new features, they said, Bjarne, it doesn't work. He'd go fix it. And we had this cycle of real programmers solving real problems with this developer saying, OK, let's go fix it. And after a while, you ended up with C++. So it's been around for, I think, this is, the 25th anniversary of C++. So wow, how exciting. So I want to talk about the philosophy a little bit. What is really driving the development of this language? What does it expect out of you? So I have some quotes from this book called The Design and Evolution of C++. Good book. You should read it. The first one, C++'s evolution should be driven by real problems, and you don't want to get down in a quest for perfection. Basically, this language is designed to solve real problems that real programmers like you are going to run into, and not necessarily the best way. It tries to do a good job. It's not intended to be perfect. There are some sloppy edges, but it works. And because it is driven by real problems and real design issues, you can solve real problems with it. If you think that's a good thing in a language, I personally do. I think it's good to have a language that can solve problems. Then C++ is a good choice. This is probably the one that you've seen the most. Don't try to force people. C++ gives you so many choices that your question should not be, well, how do I do this in the language, but more of which of these hundreds of options is the best choice for me. It really trusts you as a language. It will give you an incredible amount of flexibility, even to the point where it will let you make the wrong decision. I've always thought C++ is a language that will let you ride a bicycle without a helmet, because that one time you need to go under a bridge, it's exactly a quarter inch over your head, you won't have your helmet knock you off your bike. You do have to worry about a lot of risks, but in the end, you'll have more flexibility than you will find in most other languages you see. And finally, I think the most important one is this. C++ makes programming more enjoyable for serious programmers. The two things here are serious programmers and more enjoyable. This is a professional language. It's used in industry everywhere. It's very fast. It's very efficient. It has a bit of a learning curve. It is kind of tricky to get into the language, but once you've got it, the second part, the more enjoyable, is so true. This language is fun to write things in. Once you've got it down, you will actually step back from your program and say, wow, I just wrote something that took every single word out of this set that I had made that has contains a specific letter in a single line of code. Or I loaded all of the contents of this file into my set, one line of code. Or I just wrote a template that is a multi-dimensional array of any dimension I want. Those are not trivial accomplishments, and you can do it with this language. It's fun, it's a great language, and if you think that this sort of philosophy is what you want, where it will trust you, it will really let you make the decisions rather than forcing you into any one paradigm, learn C++. I think you'll love it. So, philosophy. There's lots of it. But, I'm not here to teach a philosophy class. I'm here to teach you about C++. So let's get down to some of the details. What does this language look like? And the first thing I want to do is talk about what genlib.h has. Since day one, you probably have seen things like this. Pound include genlib, very first line, right here. What is in this genlib thing? Has anybody actually looked at genlib before? Anyone pulled up the genlib file and looked inside? No one? OK. Well, if you look inside genlib, it looks mostly like this. There are basically three important lines you need to know. Pound includes string. So we taught you about the string class as though it was a built-in type, like int or double. It's a class. It's like any other object, like a vector or a map. You do need to pound include it. We just took care of it for you because since you use it everywhere and it's easy to forget and you can get some pretty nasty compiler errors if you don't include it, we thought, we'll be nice, we'll do that for you. The second thing is this error function. You've seen error, genlib just gives you a prototype for it. The end. But this last one right here, using namespace std, using the standard namespace. What on earth is this line? I mean, it looks almost like, English sentence. Oh, compiler, make my code work. What's going on here? Well, I'll go show you. Suppose I have this little program down here. Can anybody see this? So I just want to pound include iostream and pound include string. If you notice here, I don't have genlib. And I'm going to make a string and print it out. So the question is, when I say string my string, what am I referring to? Well, when this happens, the compiler says, well, go look for something called string. And when we pound included string, it put it inside this big bucket of something called namespace standard. The idea is that the real name of string is standard string. The real name of cout is standard cout. The real name of endl is standard endl. It's just so that if you make your own versions of those things, it doesn't have the same name as something in the standard. It won't conflict, and your program will still compile. But the problem is that if you try to run this, what will happen is that the compiler says string, looks up here, and hits this wall. It says, oops, that's inside the standard namespace. I can't go in there. And you'll get this really nasty compiler error, something like string's not defined, cout's not defined, endl's not defined. Now, most of the time when you're programming, you kind of want things like cout and string to actually exist. And so rather than saying you have to call it standard string, standard cout, standard endl, you can introduce this little phrase right here, using namespace standard. And what this says is take this wall and get rid of it. It's like, Mr. Compiler, tear down this wall. And the result is that this kind of barrier just gets a little bit kind of transparent. It's all still included inside of the standard namespace, but now it's accessible. So when you say string, it goes, oh yeah, that thing, and actually compiles. Now, most of today, I'm not going to be hitting you with C++ and saying, you must know this, you must know this, you must know this. There's just not enough time to go over everything. But this little line might be something worth committing to memory, because it's the most noticeable change you'll see when you stop using genlib. If you don't put that line in your code, you'll get lots of compiler errors, and it'll just kind of scare you. So if you put this line in, I'd say 90% of your compiler problems will go away. So that's that line. That's genlib. And if you want to take a look, if you write this code, you've basically replaced all of genlib. The first header file you have to include is this one, cstdlib, the C standard library. I'm thinking that when they invented the C programming language, it cost them several $1 million per vowel or consonant they put in their header files. So they put it as small as possible, it's still readable. And the idea is that you have these two lines, the important ones, pound include string, using the standard namespace. And then right here in this error function, you just print everything to cerr, which is like cout, it's just designed for error handling. And you call exit -1, which says, quit this program, report some error to the operating system, and we're done. This is it. This is all that is contained in genlib. And the only two important lines are these ones right here, including the string class and using the standard namespace. And if you do that, and you get rid of genlib, you're going to be in perfectly good shape. Now, genlib is probably one of the easier ones, but what about some of these other headers you've seen? Well, I could go into some detail about all of these, but I just don't have time. And I really wish that I could show you, here's how this works, here's how this works, but I just kind of give you a quick overview today, just to show you what you'll need to know if you want to get off these libraries. The first one is strutils.h. This is the one that gives you string to integer, integer to string, string to real, convert to uppercase, convert to lowercase, etc. Behind the scenes, most of this stuff is backed with this class called a string stream. You've seen if streams, you've seen OF streams, you've seen cout. They're all streams. You can do less than, you can do greater than, greater than. The point of the string stream, it does the same thing, except that it writes to a string buffer. So you can take some integer, dump it into a string. That's your integer to string function right there. There's a couple other things you can do with it we use for doing conversion between strings and other data types like integers. So you might want to look into that if you're going to play around with it. As for convert to uppercase and convert to lowercase, there's these functions 2upper and 2lower that take individual characters and convert them to uppercase and convert them to lowercase. Just for loop over your string, call that function every time. Presto, your string is in uppercase. That was pretty straightforward. In case you're interested, in CS106L, we actually wrote some of these functions. If you want to have a working implementation of strutils.h, if you go to the CS106L website, under the code section, there is a working implementation there. So if you want to keep using these things, just go download that file, take a look at it, play around with it, and it should work.
So if we wanted to set up a sort of coding environment on some Linux machine that doesn't have any of the standard like PC Mac starter files from this, we could use that?
Yeah, no, it uses only standard C++, so it'll compile everywhere. And it works pretty well. I mean, I think we only defined a few of them, but you can see how they work, and you can define it for, we give you string to integer. You can do string to double or string to real pretty easily just by changing a couple types around. Yeah. OK. This is probably the big one you're going to miss, simpio.h. How many of you have ever played around with raw C++ input functions before? Yeah. So they're kind of nasty. I've always thought that this thing called cin, which is the counterpart of cout that does input, is kind of like a rose, which is it's very sweet, it's very delicate, but the second that you break it, it stabs you with a thorn and it hurts a lot. Really, you have to think of this as probably one of the most powerful, one of the hardest to use input libraries out of any programming language you will see. So we gave you this simpio library just to take care of all these things for you so you don't have to worry about it. It turns out that the way it works, everybody remember getLine? You can use it to read a line out of a file. Well, you can use getLine on this cin stream to do input reading. Read a line as text, use a string stream to convert it into an integer, plus or minus a couple extra things. That's getinteger. Again, if you go to the CS106L website, there is a working implementation of this. If you do want to consider doing C++ beyond this, this actually is a pretty good set of input functions. You'd be surprised how many people don't actually know how to write these things. So go play around with it. Have some fun. See what they do. And that way you can continue using the coding conventions that you've seen, but by using only standard C++. What about random? Well, the random functions in C++ are pretty simple. There's two functions, rand and srand, random and seed, the randomizer. Again, consonants are expensive, vowels are expensive. And rand gives you random integers in the range 0 to rand max. So if you want to get a random double, you want to get a random integer, a random Boolean, just take the number in that range, scale it down to 0, 1, scale it back up, translate it, etc. It turns out this is probably the easiest one to rewrite from scratch. You just have to be a little bit careful of how you do your bounds checking, but it's not so bad. The header file for that is C standard library, but you can probably build this one up from scratch pretty simply. The one that you actually are going to be missing is this one, graphics.h and extended graphics. Unfortunately, C++ does not have a standard graphics library. It just doesn't exist. And there's a couple reasons. One, it's very hard to standardize graphics. You have to make sure something that works on every single platform, which is very hard to do. And also, if you're writing C++ code for a microprocessor where you don't have graphics, it would kind of be difficult to support the library. So there's no standard C++ equivalent, but I bet you this program that I'm using right now is written in C++. Clearly, it's got some kind of graphics. Most of this is from third-party libraries. I do some Windows programming, so I use the Win32 API, which does some graphic stuff. There's a whole bunch of cross-platform ones like OpenGL. You can do X Windows system. I think Mac is something called Carbon. I might be wrong about that. Cocoa, Carbon. Yeah. There's a lot. In short, you won't have trouble finding it. You won't have a standard library that does it for you. So shop around with this and take a look around. The ones we give you are pretty nice. I might tell you how they work, except that I actually don't know because it's really, really, really hard. So go take a look around and you'll find some ones that are quite nice. Now, everything I've shown you up to this point are simple things like how to read input, how to convert to a string. Things that, while they're nice, while they're important, are not going to make or break your program. The thing that is really going to make a difference are these ADTs. The vector, the set, the map, the stack, the queue. Those are important. If you don't have a map, the number of things you can do in a program kind of just drops exponentially. It's really impressive how much you need these data structures. The good news is that C++ not only has very good support for these data structures, it has probably the best library in any standard programming language that does these things for you. It's something called the Standard Template Library, which is the STL. Now, for every single container class you have seen in this class, all the ADTs, you will find them in the STL. The naming might be a little different. The syntax is a bit weirder, but conceptually it's the same thing. A vector is a vector no matter what language you write it in. A map is a map. Stack is still LIFO. Queue is still FIFO, etc. The STL on top of that gives you these things called algorithms, which I will show. I'll kind of talk about this in a little bit. Basically, it's the best thing since sliced bread. I'm not kidding. It's really wonderful. It's really amazing, and I'll talk about that in a little bit. But the STL is one of the major features of the C++ standard library. It's brilliantly designed. It's it's not necessarily the most intuitive thing, but once you get a handle of it, it's very powerful. The way you can kind of visualize what this looks like is kind of like this somewhat pyramid-ish structure. At the very bottom, you've got containers, your data structures. This is your vector, your map, your set. You have iterators on top of that. Now, you've all seen iterators in this class. You've seen map iterators. You've seen set iterators. The STL is basically all about iterators. Every single container class has iterators. So you can iterate over a vector, you can iterate over a map, you can iterate over a set. And those work to build these things called algorithms, which again I'll talk to you later, where they're just functions that operate on ranges of data. And it's really impressive what you can do with these things. I'll show you a little bit of that later. Now, these container classes, the good news is that the names are pretty similar. Basically, take the 106 version, make it lowercase, you've got your STL. So big vector turns into little vector, big map turns into little map, etc. The one exception is grid. There is no STL grid class. It's very easy to make one, though. All you have to do is just take a vector and do some math to wrap a two-dimensional container into a one-dimensional one. In fact, that's how our grid works, so you'll have to build that one. But otherwise, everything's taken care of for you, and that's quite nice. Again, they have the same fundamental abstractions. You know how to work with the stack, so you know how to use the STL stack just with a little extra syntax. The big thing I will say up front, the emphasis in the STL is on speed. In fact, they are designed to be really, really fast. And that means that their notion of safety is safety. Yeah, good one, good one. So what this means is that you'll have to do your own bounds checking. When you're iterating, you'll have to make sure you don't walk off the edge of your container and stuff like that. And one of the major reasons we didn't go over the STL in this class is just that, which is if you're trying to figure out how to work with the vector, it's really bad if you also have to worry about doing your own bounds checking. If you're working with a map and you have to use the STL map, you probably will never want to use another map for the rest of your life. It's pretty complicated. But the point is that this is what you'll see in the professional environment because it's a very good library and it's very fast. I just want to give you a quick example of what this might look like. So this is a program I've written using the CS106 vector. I just want to go change it to use the STL just to show you it's the same thing with a little bit of different syntax. The first thing you have to do is say, well, this vector.h we gave you, so you have to change that to the standard vector, which is vector in brackets. OK, let's see. Number of characters we've changed so far, 3 characters. Next thing, the big vector becomes little vector. OK, 4 characters. The only really big difference is this add function. Anyone want to guess, who isn't in my class, what you would call the function to append something to the end of a vector? Anyone want to take a guess? Append? That would be nice. It's actually called pushback. There's actually a good reason for this. It means that all of these different containers have similar function names. Pushback, append, potato. OK. Anyway, so that's probably about 10 or 11 character changes. And then to loop over the thing, it's exactly what you've seen before. There is a size function. There are brackets, so you can go and iterate. You can go and access things. The result is that, as you can see, it's not that different. I mean, there are a couple subtleties that I didn't go into here about how the vector in the STL behaves differently from the vector you've seen. But overall, it is the same container. The other one I want to call your attention to is the STL map. So if you work with the STL, you need to know two containers, and the rest kind of follow from there. If you know vector and you know map, you've got the whole thing down. The STL map is like our map, except that instead of going string to some value, it's any key type you want to any value type you want. So you can map strings to ints. You can map ints to strings. You can map stack of q of int to vector of double. I don't know why you would, but you have the ability to do so. The problem is that the interface on map was probably designed by someone who didn't like people. It's really hard to use. Anyone who's used it will tell you that. Once you get the hang of it, though, it's pretty intuitive. And the result is you have a very fast map container that really is going to make the backbone of any programs that you write. It's quite a useful class. So again, I don't expect you to memorize every single bit of syntax here, everything I'm saying. Just kind of keep in the back of your mind, this is what you want to look into. The map is one you do need to know. So go take a look at that one if you want to pursue C++. Now, iterators. So the iterators you've seen in this class are very nice. They're very well behaved. They're like warm and fuzzy. You're like, oh, has next, next, has next, next. Nope, no has next, I'm done. STL iterators are designed to look like pointers. Now, you might wonder why anyone would voluntarily make something look like a pointer. There's very good reasons. What this means is that they're about as smart as a pointer, which means they know nothing. So if you want to iterate over a range, you have to have two different iterators. You have to say, start here, stop there, keep walking forward until you get there. And admittedly, well, it's more work. But it's very useful because it means that if you want to iterate over a 20-element slice out of a 400 million element container, you can do that. Try doing that with our libraries. You have to go iterate all the way up to the start, then keep iterating more. The other big thing you need to know about the iterators is their read-write. So you can actually crawl over a container and update the values with an iterator, something you cannot do in our libraries. It's a bit more work. The syntax basically looks like pointer reading and writing, but the result is that they're much more powerful and they're a lot more flexible. So here's a quick example. I just wrote some code here that uses a vector iterator. The thing to take a look at is this bit right here. OK. So basically, there's a couple parts to point out. I just want to show you this, so if you see this later on, you'll get it. Can everybody see this? The first thing is that this begin function. We call it iterator. They call it begin. It just says, give me a start iterator. Since we need two iterators to define a range, we keep going until we hit this iterator called end, which just means stop. To move the iterator forward, has next and next would be too nice, so it's plus plus. And then to read from an iterator or write to it, you just dereference it. So you can actually do star iterator as if it's a pointer, which in many cases it actually is. That's kind of the gist of what this looks like. There's a couple more nuances and subtleties. But if you keep in mind that when you're looking at STL stuff, just treat this like pointers, it will make a lot of sense. Last thing I want to talk about are algorithms. These things are amazing. So the idea is that everything's got iterators. So if you write functions that work on iterators, they will work on any container type. So if you want a binary search over a vector, you call binary search. It's a pre-written function. You want to sort something? Great, go call sort. You guys seen permutations before, right? You have to go do recursion, pull something in the front, permute the rest, stick it back on, that sort of stuff. STL, you can do it in a while loop. You can while next permutation something, come with every single permutation, and you don't have to write a single recursive function ever. Pretty nice. These sorts of things, there's, I think, 75 different algorithms. Everything from permuting to searching to sorting to transforming to rearranging to sorting to splitting. You name it, there's probably an algorithm that does it. And if you play around with the STL, you get to see all this stuff. And it's a lot of fun. Now, I've just been showing you some of the libraries. That's mainly the library changes you need to know. I mean, basically, everything you want to do is still there. The syntax is a little different. Some of the libraries you'll have to write yourself, but it's all there. It's not like you have to relearn everything from scratch. But the libraries are only as good as the language is. And there's a couple language features of C++ we didn't really talk about in this class, and I just want to go over some of them because you will see them a lot in professional code. After all, I mean, you cannot use a library any more than you understand how the language works. So getting kind of a rough understanding of what this will do will make your life easier in the long run. First thing I want to talk about is const. So you've seen const before in the context of const int my constant equals 5. Just make a global constant. And saying that const makes global constants is like saying a computer is something that adds numbers. Yes, but they can also like run Windows, for example. And const shows up just about everywhere. It's the little keyword that could. And you'd be amazed just how useful this little keyword can be. The biggest thing that it does is it helps protect you against your own mistakes. If you're writing a program and you know something shouldn't change, tag it const. Because that way later down the line, if you do accidentally change it, it says that's a mistake. Compiler error, you screwed up. And it just protects you from, oh yeah, you're right. That should have been a double equals, not a single equals. Those sorts of things. You've all probably seen that the C++ compiler doesn't treat anything as sacred, like, oh, you just don't want to return something? OK. Or something like, oh, wow, you did single equals instead of double equals. Well, you're the boss. The second you try to break const, it pulls out its big ruler of judgment and whacks you on the wrist with it, like, shame on you for breaking this constness. So it is the compiler trying to help you out. Please know about this keyword. Let me give you an example. See this function prototype? Void do something takes a vector by reference. So I pass my vector into this function, and the question is, well, what's it going to hold when it comes back? Well, could be the same, could be completely empty, could be 137 copies of the number 137. You just don't know. Because in this class we've shown you, well, pass by reference can be either for efficiency reasons, because it's not fast enough, or it can also be because you just want to actually change the thing. And it's difficult to see what this function does because you have no idea which of those two it is. The idea, though, and this is something you will see in professional code everywhere, is doing something like this. If I say void do something const vector and my vector, well, that says this vector can't be modified inside the function. It's kind of like handing this thing off saying, I'm giving you this value for efficiency reasons. Don't try to modify it. In fact, you can't modify it. It makes your code self-documenting. Someone looking at your functions can go, oh, yeah, that's const. I can't possibly change anything there. And they'll be totally fine handing off, the string containing their graduate thesis to it, for example. If you had your string stored as a graduate, or if you had your graduate thesis stored as a string, which I don't know why you would ever do this, but if you see, a function that takes a string and parameter, you'd probably be a little bit worried, like, is it going to replace my graduate thesis with, hi, I don't have a graduate thesis, or what? The const is useful. The question is, if it's such a useful keyword, well, why didn't we show you this? And the biggest reason is you can't just use const every now and then. You can't say, I'm going to mark this parameter const. I'm going to say, that one's const right there. It doesn't work that way. Let's say I do mark something const. Well, that object has to know how to behave when it can't modify itself. So you have to make the entire class written const correct. And then if it has any data members that are classes, that class has to be const correct. You get this exploding effect where you stick a single constant and suddenly every piece of your code is marked const. Now that's a good thing, because it makes your code self-documenting. But the point is, it's an unnecessary language complication. When you're trying to write the PQ class, you should be worried, how do I build a chunk list, not, oh, is this function const? Is that data member const? Etc. So in the professional world, you will see it. But here we just thought it makes things too complicated. We'll give it a pass for right now. Another big one, object copying and assignment. So you've seen disallow copy. It says, don't copy this object. And feel nice. It's not standard C++, but I've been told that Google actually has a macro that does something just like this. So you're programming the same way Google people do. The problem, though, is that if you're trying to write a PQ and it can't copy itself, it's a little bit frustrating. I mean, think about it. You make some PQ. You can make a vector copy. You can make a map copy. If you can't make a PQ copy, you're going to be wondering, well, why not? So it turns out C++ lets you actually redefine the way that copying works. So these two functions here, called copy constructors and assignment operators. And while it's very useful to know how to do this, there's a major reason we didn't tell you about it in this class. And it's because it's really, really hard. I think I spent in 106L an entire week going over this. So we don't have a week to tell you about how to do this. Here's a list of some of the things you have to keep in mind when writing these functions. You have to make sure to clean up your own memory, not to clean up memory you don't own, to clean up all of your memory, to copy the other object, to copy the other object correctly, to handle these weird edge cases, to follow the same rules that C++ syntax dictates. There's an awful lot of stuff going on there. And to expect you to get all of this right when you're worried about your PQ is just too much. In all seriousness, it really is. I mean, imagine it's the day before it's due. You've got the PQ working beautifully and doesn't copy right. Well, what does that tell you? It means you've written your copy function wrong, but you totally understand the major point, which is this is how you build a priority queue. This is a chunk list. This is a heap. This is an unsorted vector. That's what's actually important, not building stuff like this. But when you're in the professional world, you do need to do some extra work to make sure to make your objects copy correctly. So you should look into these functions a little bit. But again, to stress, the stuff you've learned in here, the actual here's how you go build these data structures, is more important than these little syntactic nuances you've got to be aware of. So one more thing. This is pretty cool. So I have this little code snippet right here. I make a string, and I say my string is equal to this is, and then I tack onto it a string. I'm going to go iterate over this entire string. In every step, I'm going to print out the current character. So this is just print out the string one letter at a time. Let me go highlight a few things. OK. Why is it legal to plus equals a string with something else? Why string but not priority queue? Why are we allowed to do this? It's not an integer. It's not a floating point type. It's a string. It's an object, and we just called plus equals on it. Why does cout let you do less than less than? What does that mean? Why do streams let you do that but nothing else? And why can I read a string with brackets even though it's really an object? Well, the thing is, at a high level, we all know what it means to add something to a string. It means take something, stick it on. You know what this less than it means put into a stream. You know what the brackets means. And so you can tell C++, I want to define these operators for my classes. It's a technique known as operator overloading. Basically, all you do is write functions that are called operator and then whatever the name of your operator is. So operator equals, operator brackets, operator less than, operator plus plus. And it just is a syntax convenience. It makes it so you can write code that looks more intuitive, that does something complex behind the scenes. For example, if I write my vector bracket I, it's not like, oh, it's a bracket, it's much faster. It really just means call the function called operator brackets. So again, it's a convenience and nothing else. If you treat it as any more than a convenience, you can kind of hurt yourself with it. You can overload basically every operator in C++. You can overload things like bitwise XOR with assignment. You can overload the XOR operator. You can overload parentheses, and, comma. All these operators most people never use. The ones that you see most frequently, though, are these ones. Overloading operator less than for stream insertion. You can actually make it so that you can make a vector class that can print itself out to the screen. Kind of useful. The assignment operator, operator equals, the less than operator for comparing things, and the parentheses operator. Yes, you can actually overload parentheses. It's pretty cool stuff. It's actually for something called functors, which is really awesome. If you do play around C++, this is definitely something to keep in mind, because it really will make your life a lot more enjoyable. Now, I think more than any other language feature of C++, except possibly multiple inheritance, this is the most widely criticized feature of the language. And the reason is that you can make things that make no sense legal, like defining the modulus operator for two PQs. Like my PQ mod my other PQ. Anybody here think of a sensical interpretation of what it means to mod one PQ by another? If you do, please send me an email or shout it out right now, because I can't think of one. But you can make it legal. I don't know why you would, but you can. And the point of this is, if you think about it, recall the philosophy. Let the programmer make the choice, even if it lets them choose wrong. You can do this. You probably shouldn't do it. But by giving you the opportunity to do so, it means that when you really do need to write a class that has a modulus defined, you can do it. It's flexibility. It means you have to make sure that what you're doing makes sense, but it's flexibility. You've all just finished Pathfinder, right? Did anybody here templatize the chunkless PQ by any chance? Anyone? You guys are smart. OK. Yeah. Well, here's the thing. Let's say I write something that says A equals B. OK. What does this mean? It says assign B A. Now, what if I write this in a template function? I have a template of some unknown type, and I just say A equals B. Well, what's it mean? Well, if it's an int, it means take the int and copy it. If it's a floating point number, it says take the floating point number and copy it. If it's a string, it means make a string deep copy. The point is that every single time you use the same syntax, A equals B, but the result is different, and it's always the correct result. This is what you can get with operator overloading, the ability to take code and make it look right for every single class, so that in templates you can just call the function and you're guaranteed it will work. So that's just a quick tour of some of the language features. I know this might seem like an awful lot. I've been going very quickly through it. But I just want to conclude by saying, well, so what? I just hammered you with a lot of language features, a lot of syntax, a lot of libraries. What's the point? Well, the big point to take out of this is that C++ is big, but it's also a very powerful language, and it's a very expressive language, and I think it's a very beautiful language. The features that you've learned in this class will go anywhere you want them to. And if you want to take your coding skills and apply them to C++, then you can, and you have this flexibility, And you really have this gift. What you've learned in here is something most people never learn. It's how to make a computer solve a problem for you. And that's a skill that's going to follow you for the rest of your life, no matter where you take it. If you're interested in C++, I have a huge number of references here if you want to go see them. But the point is that if you want to solve a problem with a computer, you need three things. You need, first, programming skills. You all have that. You need a good idea. I don't think I have any good ideas for programming. If I did, I'd probably do them myself. But if you do have a good idea and you want to make $1 billion with it, the last thing you need is a programming language. And hopefully, this little quick tour of C++ has kind of showed you this is what this language is. It's a tool for solving real problems that trusts you, and that means that overall you'll have fun doing it. So if you want to go and run with this, if you want to say, I'm a good programmer, I can do this, learn C++, I think you will love it. I think you'll enjoy it. I think it will be some of the most fun you will have sitting in front of a computer. So have fun with this stuff. That's the whole point of this. If you're in this class, I hope you enjoyed it. I hope you said, oh yeah, I can make a computer solve something. I can do graph algorithms. I can do graph theory. I can make data structures. I can make a computer program that plays Boggle better than I ever could or anyone I know ever can. Have fun. That's the whole point of this. And if you want to do it in C++, come talk to me and I will go give you some references. So enjoy. Good luck on the final. And I probably will see you around on Friday for the final. So enjoy.